Good afternoon, students. Myself, Dr. Prasad, Associate Professor in Physics, CC University of Technology and Engineering, Tadepalligudi. Today we are going to discuss about the mid-2 portion of the syllabus. Let we consider the mid-2 portion: pumping mechanism, ruby laser, helium-neon laser, direct and indirect band gap semiconductor, optical transitions in bulk semiconductor, construction and working of laser diodes and their applications. This is the fourth unit of mid-2 syllabus. Injection electroluminescence, construction and working of LED, characteristics of LED, internal efficiency, extraction efficiency, external efficiency, power conversion efficiency, responsivity, IV characteristics, double heterostructure and their importance in LEDs, LED types, surface emitting LEDs, edge emitting LEDs and their applications of LEDs. Next, photodiodes. Introduction, construction and working principles of PN photodiode, PAN photodiode, avalanche photodiode and their IV characteristics, photovoltaic effect, that means solar cells, construction, working, fill factor and efficiency of the solar cell. Now, today we are going to discuss about the important components of laser source. One is the active medium, pumping source and optical resonators. Active medium is one of the important component in laser device. Active medium means the medium in which the population inversion takes place is called as active medium. The medium in which the population inversion takes place. Suppose let we consider the laser system. Let we consider the laser system. This is an active medium. This is an active medium. The medium in which the population inversion takes place is called active medium. Suppose let we consider helium-neon laser. Helium-neon laser. Helium-neon gas mixture acts as a active medium. Here neon atom is the active centers to participate the laser action. So in this device helium-neon gas mixture acts as a active medium. Next, pumping source. Pumping source. This is the pumping source for active medium. Pumping source mean to pump the atoms to excited state. To pump the atoms to excited state to achieve the population inversion condition. That is the pumping source action. Next, optical resonator. Optical resonator. In the active medium, both sides we are constructing have optical resonators. Optical resonators mean one of the mirror is 50% reflecting mirror, another one is the 100% reflecting mirror. The both are acting as a optical resonators. Optical resonators to enhance the energy of the light and to amplify the light, such it is called optical resonators. Here the 50% mirror and 100% reflecting mirror. In the 100% reflecting mirror, the total light reflecting back and 50% is passing to the 50% reflecting mirror and remaining it's into the active medium. It is the process of multiplication, again back to 100% reflecting mirror and then go to 50% reflecting mirror, it will be emerges out. The sustainable output we can be obtained from the laser source, that is the source of the optical resonators. So the active medium, pumping source and optical resonators, three important components in the laser system. Next, helium-neon laser. The construction and working of helium-neon laser and advantages, disadvantages and applications of helium-neon laser. Every laser working on the principle of population inversion, right? The population inversion is the condition for population inversion. Population inversion means more number of atoms in the excited state to compare the ground state. We can compare to the ground state with an N2 greater than N1. That is the condition for population inversion. Population inversion means more number of atoms in excited state. Let we consider two-level energy system, that is E1 and E2. This is the two-level energy system. The population of atoms in the ground state energy level N1, the population of atoms in the excited energy level N2. Here the condition N2 greater than N1. N2 greater than N1 is the condition for population inversion. To achieve the population inversion is the pumping mechanisms or various pumping mechanisms are used to achieve the population inversion condition. Generally, let we consider a ruby laser. Optical pumping is the pumping mechanism used for the population inversion, and helium-neon laser electric discharge method is used for the pump the atoms in the excited state to achieve the population inversion. Semiconductor laser direct conversion method is used for the to pump the carriers in the junction region and to recombine to produce the laser. Is the direct conversion method is the pumping source for the laser diodes. Here the pumping source is used for to pump the atoms to the excited state to achieve the population inversion condition. Once population inversion condition is achieved, the more number of atoms in excited state, that means N2 greater than N1. So the photon is incident on that system. Here the photon is absorbed by the excited state atom. It emits the 2 photons instead of 1 photon. Two photons are, these are the two coherent photons. It emits from the one transition. One photon is released before the absorption, one is the interaction photon. Though it recombined, it is de-excited to the ground state, it emits the 2 photons. Two are the coherent photons. Here 2 photons stimulate the another 2 atoms in the excited state, it released in 4 photons. These 4 photons stimulate the 4 atoms in the ground state, it emits the 8 photons. So the finally 2 power 1, 2 square, 2 cube and 2 power 4 and so on. So photon multiplication is occurred, and here the device is in gain. So that is the principle of the laser action. So laser action principle is involved in population inversion. Once population inversion is achieved, laser action will be started. The working principle of helium-neon laser. Now helium-neon laser working principle is the population inversion condition. Population inversion condition achieved, the helium-neon laser works. Here helium-neon laser, here helium and neon is the gas mixture, is taken in the discharge tube, a long discharge tube of the 10 centimeters length. Here the helium is consist of 10:1. That means 10 millimeter of Hg helium is inserted in the quartz tube and 1 millimeter of Hg neon is inserted. So the helium-neon gas mixture is in the ratio of 10:1. This is the 10:1 ratio of the helium-neon gas mixture. This is act as a active medium. The both are the active medium. So in this glass bulb, it will be connected to the power supply, high tension power supply. One of the terminal acts as a cathode and one of the terminal acts as a anode. This is acts as a electric discharge to provide the helium-neon gas mixture. Electric discharge means electric current passes through the gas medium, that is called electric discharge. The both quartz bulb, the both ends are sealed with brevistor windows to produce the plain polarized light. These windows are produced plain polarized light. In that plain polarized light, in the direction of the plain polarized light, the perpendicular to the plain polarized light, we can arrange the 2 plane mirrors. One of the mirror is called 100% reflecting mirror, and one of the mirror is called partially reflecting mirror. Here this is the 50% reflecting mirror and a partially reflecting mirror, and this one is the 100% reflecting mirror. Both are acting as the optical resonator. Here we can observe helium-neon gas mixture is a active medium. Electric discharge, the power supply is act as a electric discharge, and both mirrors are act as the optical resonators. Now we construct the construction of the helium-neon laser. Let we consider a quartz bulb of length 10 centimeter. We inserted helium gas at the 10 millimeter of Hg and 1 millimeter of Hg neon is fixed. So it is a combination of helium-neon 10:1 ratio. The brevistor windows are placed at the both ends of the quartz bulb. It acts and produced as a plain polarized light, and both of the both of the brewster windows to provide the two optical resonator. One is the 100% reflecting mirror, one is the 50% reflecting mirror. So working, let we consider the power supply is on, the electrons are discharged, the electrons are discharged from the cathode. Here the electrons are discharged from the cathode and reaches to the anode. In the process of their journey, it collide with the helium or neon atoms, and maybe collide with helium or neon atoms. So helium is a lighter particle than compared to the neon. So the electron collision with helium, the total energy of the electron, here the collisions are inelastic collision, the total energy of the electron transferred to the helium. So the helium atom goes to the excited state. But neon is a heavier particle, so that much of amount of energy is not sufficient to rise to the excited state. So helium is help to neon. So in the process of ground state, the helium in the excited state, after completion of their lifetime, it grows to the goes to the ground state. In the process of their journey, the helium collide with the neon atom to transfer the total energy to the neon. So neon atoms rise to the excited state and to participate the laser action and to produce the laser output. This is the working of helium-neon laser. Helium-neon. This is the energy level diagram. Let we consider an energy level diagram. First, electric discharge is passing through the gas bulb, discharge bulb. The helium atoms, here the helium atoms, helium atoms rise to the excited state by collision with electron. Here the electron energy, total energy of the electron transferred to the helium. Helium is raised to the excited state. Helium is raised to the excited state. Some of the helium atoms rise to the excited state F2. Some of the helium atoms rise to the F3 state. Both are the excited states and metastable states of the helium atoms. Both are acts as the metastable state. Metastable state mean the state which are having longer lifetime than compared to the excited state and lesser lifetime than compared to the ground state. Here the lifetime at atoms is 10 to the power of minus 3 seconds than compared to the excited state which are having the longer lifetime. After completion of this lifetime, the helium atom de-excited to the ground state. In the process of the ground state, it collide with the neon atoms in the ground state. And helium collide with the neon atoms. The total energy of the helium transferred to the neon. So the neon atoms goes rise to the excited state. Here helium and neon both are the excited energy levels are coincident. So let we consider helium-neon gas mixture. What we should prepare the helium-neon gas mixture? Both energy levels are excited energy levels are coincident. So let we consider as a helium-neon gas mixture. Here helium helps to neon to rise to the excited state. Suppose neon atom, suppose helium atom, F3 level helium atoms collide with the neon, so neon atoms go straight to E6 energy level. Suppose F2 energy level helium atom collide with the neon, so neon atoms go straight to E4 energy level. This is the energy level difference, 20.16 electron volts. This is the 19.86 electron volts energy difference. The energy difference. So 20.16 electron volts excited energy level and 19.86 electron volts excited energy levels. The both neon atoms. So some of the neon atoms goes to the E6 energy level, some of the neon atoms goes to the E4 energy level. Here the both states E6 and E4 acts as the excited energy levels. That means both are acting as a metastable state. Some of the neon atoms goes to the E5 state. This is the E5 state. The emission of the light energy 3339 angstrom, that for 3.39 micrometers. It is not useful, it is infrared region. So some of the neon atoms rise to the E3 level. This is the important transition. It emits the 6328 angstroms laser output beam. It will be emitted. The wavelength of the laser output is 6328 angstroms. 28 angstroms. Some of the neon atoms from E4 level to the E3 level, it emits the 1.15 micrometers. That means 11,500 angstroms wavelength radiation. This is also the infrared radiation. The neon atoms in the E3 level, by the spontaneous emission process, it emits the photon of wavelength 0.6 micrometers. It rises to the E2 excited state. The neon atoms collision with walls and de-excited to the ground state neon atoms. The process will be begin. The helium atoms in the excited state and collide with the neon atoms. The neon atoms rise to the excited state and to participate the laser action. Here helium-neon laser is a 4-level laser system. How to consider 4-level? This is the one transition, one excited to ground state, one transition, and excited state to another level, E2 3 seconds transition, E2 to E1 third transition, E1 to E6 is the first transition. First, second, third and fourth. So, this is the 4-level laser system. Helium-neon laser is a gaseous laser and 4-level laser system. What is the advantages of helium-neon laser? Helium-neon laser emits laser light in the visible portion of the spectrum. Let we in the helium-neon laser system, the output of the laser beam is 6328 angstrom. This is the visible region. That is the one of the advantages of the helium-neon laser. High stability, durability, low cost, operated without damage at higher temperature. So, these are the main advantages of the helium-neon laser. Next, disadvantages of helium-neon laser. Only the disadvantage of low efficiency, not in the gaining medium. The medium is not in the gaining medium. Helium-neon laser is a limited low power tasks. So, these are the disadvantages of the helium-neon lasers. Applications of helium-neon laser. Helium-neon laser used in the barcoding system. Helium-neon laser used in the scientific instruments. Helium-neon laser in the college laboratories or in many of the industries, high surgeries. Helium-neon laser is used in the many of the applications, military and communication field, and also barcoding system and energy storage devices. So, these are the number of applications of the helium-neon lasers. Next, direct and indirect band gap semiconductors. Next topic, fourth unit. The first topic is direct and indirect band gap semiconductors. The semiconductors based on the EK diagram, the semiconductors classified in two categories. One is the direct and indirect band gap semiconductors. The based on the indirect and direct band gap semiconductor. E that we know E is equal to h cut square k square by 2m. This is the relation between energy and momentum. Here h cut square k square is represents the h cut square k square is represents the momentum. So, that is indicate p square, and E is equal to p square by 2m. So, here E is directly proportional to k square. Let we consider E is proportional to k square. Here we can observe h cut square by 2m is the constant. Let E is equal to akx square. This is represented as the parabola. Let we consider EK diagram is the shape of the parabola. This is an EK diagram. This is an EK diagram. This is the value of E. This is the value of E, and this is the value of K. This is an EK diagram. Let we consider an EK diagram. This is the conduction band. EK diagram variation in the valency band. This is the EK diagram variation in the conduction band. Here we can observe the maximum value of the valency band, the minimum value of the conduction band occurring at the same value of the K. That is called direct band gap semiconductors. In the case of direct band gap semiconductor, the maximum value of the valency band, the minimum value of the conduction band occurring at same value of momentum. That is called direct band gap semiconductor. Here here the electron they recombined with hole, here energy and momentum both are will be conserved. Here we can observe both are having the same momentum and are having the, even once electron is recombined with hole, the excess energy released in the form of photon. So energy will be considered, both will be considered. The recombination is takes place. Once the recombination is takes place, the both energy and momentum is conserved in the case of direct band gap semiconductor. But suppose third and in the semiconductors, third and fourth group elements is considered as a direct band gap semiconductor. For example, gallium arsenide, gallium is third group and arsenide is fourth group, and gallium arsenide, indium phosphide, third and fifth group, indium aluminum gallium arsenide, indium aluminum gallium arsenide is acts as a direct band gap semiconductors. These direct band gap semiconductor used for the fabrications of LEDs, laser diodes, photocells and solar cells. Next, indirect band gap semiconductor. Let we consider an indirect band gap semiconductor. Here this is the EK diagram, this is the value of E, this is the value of K, this is the value of K. This is the K, this is an E. Here we can observe the maximum value of the valency band, the minimum value of the conduction band does not occur at the same value of momentum. So this is called indirect band gap semiconductor. Let we consider this is the electron in the conduction band, the hole in the valency band, both are having the different momentum. Here this momentum is K2, here this momentum is K1. So both are having the different momentums and different energies. How to recombine electron and hole? Here the electron and hole recombined, the two principles are conserved. One is the energy and one is the momentum. Here the both momentums are different. So here in the higher momentum value, this is in the lower momentum value. In that process, the electron loses their energy to the crystal lattice in the form of phonons. Phonon is the lower energy photons, it released in the form of heat to the crystal lattice, and the excess energy is compensate, and the excess energy lost to compensate the momentum to recombined with the hole. It emits the light photons. This is called an indirect band gap semiconductor. Generally, fourth group elements in the periodical table, fourth group elements are considered as a indirect band gap semiconductor. Let me silicon, germanium acts as the indirect band gap semiconductor. In the indirect band gap semiconductor, the recombination takes place, it emits the phonons, not then photons. So it is not useful for the optoelectronic devices. Only this useful for the diodes, transistors and rectifiers is used for the fabrications of indirect band gap semiconductors. Next, light emitting diodes. The one of the important topic is the light emitting diode. Light emitting diode is a simple PN junction diode. The light emitting diode is a simple PN junction diode. This is the P region and this is the N region. This is the simple PN junction diode. Whenever the majority carriers recombined with the minority carriers, it emits the photons when current is passing through the diode. When current is passing through the diode, the majority carriers recombined with the minority carriers, it emits the photons. And that means here electrical energy converted into light energy, that is called LEDs. LED mean light emitting diode. Light emitting diode mean the electrical energy which will be converted into the optical energy. Every LED is the working of the principle of injection electroluminescence. What is the phenomena of injection electroluminescence? What is the basic principle of operation of light emitting diode? Is the injection electroluminescence. Induction electroluminescence, injection electroluminescence. Here electroluminescence mean the material is subjected to the electric field. The material is subjected to the electric field. When applying the electric field, it emits the light. So luminescence means light. So light emitted due to the application of electric field, that is called electroluminescence. Electroluminescence is the phenomena in which the light emitted from the material when is subjected to the electric field. The electroluminescence due to the recombination of charged carriers injected at the junction diode is known as the injection electroluminescence. What is the meaning of injection electroluminescence? Suppose let we consider an PN junction diode. This is the P region and this is the N region. This is the P region and this is the N region. This is the barrier. Barrier mean this is the immovable negative ions. This is the immovable positive ions. It creates the barrier of voltage V0 and it considered as an electric field E. This electric field, the further movement of the charged carriers will be stopped. Suppose let we consider an electron moves from cross the junction, the negative charge strongly refills the electron come back to the N side. Here the hole is moves to the N side, the positive charge is strongly refilled. So in this condition, the diode is biasing. Suppose let we, the PN junction diode is forward biased. So the PN junction diode is forward biased. That means the P end is connected to the positive terminal and N side is connected to the negative terminal. So electric current is passing through the diode. Here the voltage, here the applied voltage crosses to the barrier voltage. The holes are crossed to the N side. The electrons from N side to P side. That means the current used to inject the carriers inside the junction. So this current is useful to inject the carriers inside the junction. Here the current I inject the holes into the junction. Inside the electrons injected to the junction. So the electrons and holes injected at the junction. Let we consider a simple energy level diagram. Let we consider a simple energy level diagram. This is the junction region, this is the P side and this is the N side, this is the EC, this is an EV, this is the conduction band, this will be the valency band. The N side is connected to the negative terminal and P side is connected to the positive terminal. The voltage, the biasing voltage is applied, the N side of the conduction band increasing up, the P side of the valency band moving downwards. So the holes in the valency band, the electrons in the conduction band, N side is moves up, the electrons are ejected to the junction, the holes are injected to the junction region. So when the current is passing, the carriers are injected into the junction. These carriers, suppose the electrons are injected to the junction, these carriers recombined with hole, it emits the photon of wavelength h nu. This is the working principle of the light emitting diode. Light emitting diode is a heavily doped forward biased PN junction diode which converts the electrical current into light. The spontaneously recombined electron hole pairs lead to emission of light through these diodes. Suppose this is the PN junction diode, this is the PN junction diode, this is the P region and this is the N region. This is forward biased. Forward biased means P region is connected to positive terminal and N region is connected to negative terminal. The current is passing I, the current is passing, the carriers are injected at the junction, the injected carriers recombined, the injected carriers, suppose the electrons in the conduction band, the holes in the valency band recombined. Here the recombination, it emits the photon of wavelength h nu. Here the recombinations are spontaneously recombined. Every electron is recombined with hole spontaneously. This spontaneous emission leads to the photon generation in the LED. So LED is a light emitting diode, heavily doped forward biased PN junction diode which converts the electrical current into light. The spontaneously recombined electron and hole pairs lead to the emission of light to the diodes. Yes, the principle of operation. The principle of operation is light emitting diode is already discussed. Injection electroluminescence. In the injection electroluminescence phenomena is applied, the electrons and holes recombine spontaneously. It emits the photons. Next, this is the construction of p-n junction diode. This is the construction of p-n junction diode. This is the simple p-n junction diode. This is the p region and this is the n region. In the p region, the majority carriers are holes, and that in the case of p region, the immovable negative ions and holes. In the case of n region, the immovable positive ions and electrons. Here the holes are majority carriers in the p region, the electrons are the minority carriers in the n region. Here the p region, holes are the majority and electrons are the minority. In the case of n region, electrons are the majority, holes are the minority carriers. This is the form the p-n junction. Whenever the p-n junction is formed, the charged carriers are diffused at the junction, nearer to the junction region. It built the barrier. So barrier mean the p region is consist of immovable negative ions. This is the immovable negative ion. The n region is consist of immovable positive ion. This is the barrier of voltage V0. This barrier creates the electric field in the direction E. Whenever applying the forward bias mean p region is connected to positive terminal and n region is connected to negative terminal. Here holes are not to the positive side because this is the positive energy. So the forward biasing voltage is increased. It crossed the biasing voltage. Suppose silicon is the 0.7 volts for the biasing voltage. It crosses this biasing voltage. The width of the barrier will be slowly decreases. Suppose we apply the biasing voltage 0.1. The effective barrier voltage is 0.6, 0.2, 0.3, 0.4, 0.5 up to 0.7. The width of the barrier is completely decreases. The majority carriers at the p side holes crosses to the junction and move to the n side. The n side electron crosses to the junction and moves to the p side. The electrons and holes moves to the p side and n side. Here the electrons and holes are the majority carriers crossing at the junction and recombined with the minority carriers. It emits the light. Spontaneously recombined, it emits the light. Let we consider an energy level diagram. This is 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 an n-type connected with negative terminal and p-type connected with the positive terminal. We are biasing, voltage is applied. Here forward bias is applied. N-type, n-side conduction band moves upward. Because of this is the negative value, this is the negative value. So negative of negative, it is the positive energy. So the conduction band of n side moves up. At the same time, this is the positive, this is the positive. The valency band of the hole moves decreasing in opposite side. Electron moving in upward direction, the holes moving in a downward direction. So the electrons comes into the junction and crosses to the junction and reaches to the p-type region, and electrons entered into the junction and crosses to the n-type region. So here the electrons entered into the n-type to p-type. Here the electrons are minority carriers. It is recombined with majority carriers of the hole. Here the electron recombined with hole, it emits the photon of energy h nu. Here h nu is equal to Eg or greater than or equal to Eg. Here h nu greater than or equal to Eg, and Hc by lambda greater than or equal to Eg. Here energy gap is purely depends on wavelength. Wavelength is decreases, energy gap will be increases. Energy gap decreases, wavelength will be increases. This is the energy level diagram of the LED. Advantages: the LEDs are small in size and compatibility, easy to interface with any electronic devices, lower cost, high brightness, high efficiency, high reliability, high ruggedness, and high durability. These are the advantages of the LEDs. Next, disadvantages. Emission of light is incoherent due to the random motion, photons in spontaneous emission. These are the biggest disadvantages of the LED. LED is the spontaneously recombined. This the radiation is incoherent radiation. So this is the disadvantage. This is incoherent radiation mean it emits low directionality and low monochromatic nature, and also low luminous efficiency. The characteristics of LED, every LED characteristics are affected by the temperature. This is the temperature sensitive devices. This is the symbol of the LED. This is the symbol of the LED. This is the P region and this is the N region. P region means positive, this acts as a cathode, anode. This N region is negative, this is acts as a cathode. This is the common symbol of the LED. LED, light emitting diode. This is the light emitting diode. This is the in the structure of light emitting diode. This is the short terminal is acts as a P region, the long terminal is acts as a P region, and short terminal is act as a N region. This is the light emitting diode symbol. And next, applications of light emitting diode. Light emitting diode, the light emitting diodes emits the light with the wavelength range in the electromagnetic spectrum. That means every LED emits the light in the UV to infrared region. UV light are used in the water purification and sterilization of the surgical instruments. Visible light LEDs are used in the indicator lights and display boards and cellular phones, computers, information displays, flashlights, etc. Infrared LEDs are used in the remote controls. All the remote control devices are worked on the infrared regions of LEDs. That means headphones, microphones, and keyboards, etc. These are the applications of the LEDs. These are assignment questions based on the descriptive concept. Write the applications of LED. Write a short note on injection electroluminescence. Write the important components of lasers. What is the most common applications of helium-neon laser? Write the differences between the direct and indirect band gap semiconductors. These are the descriptive questions. Next, assignment questions based on this concept. These are the assignment questions based on this concept. Thank you.